So, hi everyone, thanks for letting me talk about my code, LARDON, which is a tool in Python to reconstruct liquid argon data. So, well, first of all, what is liquid argon TPC? It's the technology that is foreseen to study neutrino oscillation in the future DUNE experiment. And how it works, so a liquid argon TPC is a chamber filled with liquid argon in which we apply a uniform field, a drift field. And when a charged particle crosses the detector, it will locally ionize the argon and along its path. And thanks to this drift field, the electrons will be attracted to the anode. And if the field is uniform, then the electrons will drift at a constant speed that we are supposed to know.
No, and then, can you just make can you make it slightly bigger? If you can just increase the size. Yeah, that's much better. I don't know if you've lost the edge. Yeah, that's perfect.
Yeah, and then these electrons, so they are attracted to the anode, and then they are collected either with strips or wires along 2 or 3 projections in space and time. And in DUNE, the scale of this detector will be modules of about 60 meter long, 50 meter high, and 40 meter wide. So it's very big. And in order to be sure that the technology works, we built prototypes at CERN and we tested different technology. One of them, the one I'm working on, is called the dual phase. And it has the specificity to amplify the electrons just before they're collected in a small gaseous layer here with this device called LEM. Anyway, so this prototype, we call it ProtoDune DP. It took cosmic ray data in 2019 and 2020. Its volume was 6 meter by 6 meter by 6 meter. And you have a picture of the inside of the detector here. But due to some time constraints, we could only instrument half of it. So the surface where we could collect data is 6 meter long by 3 meter high. And it's actually made of 2 subplanes that we call CRPs here. And in the dual phase technology, we have 2 views that are orthogonal from where we collect the electrons. And these are the 2 views here, view 0 and view 1. And you have here a reminder of the convention in LARDON. And so the reconstruction, what happens, the problem is that things happen inside the detector in 3D. And what we have is only 2D projection. So the goal is to retrieve what happened in 3D from those projections. It seems not very complicated at first, but there are actually problems that make it more complex that I've shown here in this fake data, but you will see. So these are the kind of image we'll get from the data. So the color represents how many electrons we collect. Here in the y-axis is the time bin, so the time at which the electrons arrive, and in the x-axis at which position in the detector. And we have the 2 views, so the projection of here, 1 track that crosses the detector. So here it's completely ideal case, but in real life it's actually the electrons, it's a cloud, so there is some diffusion. So where the signal is maybe not that clear. And there's actually some random deposition. We can have more charge deposited here or there, so it's not as nice. In the detector, we can have channels that are either switched off, like here, or maybe too responsive. We can have random hits here and there due to, I don't know, radioactivity, noise, some photon converting, whatever. And we have the noise here, for example, a white noise that is added. And finally, we never have just 1 track, but usually many tracks superimposed. And the goal would be to find who goes with who from the 2 projections. Here we have 2 tracks that start and stop at the same time in the 2 views. So who goes with who? This is the game of the reconstruction. So the approach that is followed in LARDON is actually very classic. So first we have those images. We will try to remove the noise. And once we have done that, we will identify where the hits are. And we will build 2D tracks in each each view as lateral lines, and then try to match the tracks from the two views to build the event in the 3D. This is a fake event, now a real one. So this is one event taken in October 2019. We have 4 images, so the 2 CRPs that I talked, and the 2 different projections, the 2 views. So the y-axis now has 10,000 beams that represent 4 milliseconds of data, and the x-axis has 960 beams, which represent each 3 meters. We can see that in this event, there is, for example, here a couple of channels that were switched off. Here, maybe 2 responsive channels here. And the color represents how many electrons we have collected. And we can see this nice muon crossing. And we can, by eye, find who goes with who in terms of projections. For example, this track here would go with this one because they start and end at the same time. And they have patterns like delta rays that we find in both projections. Just for information, the tracks appears bended. It's not like we have magnetic field or whatever. It's just because we had a technical issue in the detector. So the first thing we do, as I said, will be to remove the noise. So there are 3 kinds of noise identified in our data. The first one is the white noise, some random ADC fluctuation. Second one is the coherent noise. So it's a noise that is seen by several consecutive channels at the same time. So for example, here we can see it clearly, like several channels have the same structure at the same time. And this is because some part of the detector acts like an antenna. And the third noise is the microphonic noise, which is a slow ADC fluctuation in time and space. And this is what we see here and here. It's like a crumpled sheet. So well, we see this slow moving pattern here. So I will show you how do we remove this data, but this event is too big to play with the whole thing. So we will work on the subset of the event. So this smaller part here. And in terms of practicality, so the data is stored in an NP array of dimension number of channel number time beams. And on the other hand, we have another NP array of the same dimension, which is a Boolean array. It's a mask that tells whether one point is data or noise with true or false. And as we run the filters, this mask is updated, and we consider a point being data or noise if it's above or below sometimes the pedestal RMS times a certain number that we set. So first we will remove the white noise, and for that it's very simple. We apply a low filter FFT pass. So here we can see here the raw event after it has been filtered with the FFT and the difference between the two. And we have one example of one channel. So how much ADC as a function of time. So if the low pass cut is too high, for example, we can see that nothing happens. And on the other hand, if it's too small, the waveform is very clear, but the difference shows that the FFT filter affected the signal as well. So we have to set a value in between these two. And okay, and then the next noise that we want to remove is the coherent noise. So from studies, we have found that this pattern can come in group of either 32, 64, or 320 consecutive channels. And in order to remove that, we reshape, subdivide the NP array in groups of the number of channels we want to remove. And in this new dimension, we compute the average noise for each time being, and then subtract that to the whole group of channels together. So here we can play again with the data. And we can apply either a subtractioning group of 32 channels, which is what is done here, or a 64, or 320. And we can see how the event is, for example, here, almost completely cleared from this coherent noise pattern. And finally, the last one, the microphonic noise. So this noise is the pattern is a slow oscillation of the pedestal in time and space. We have tried many things to remove that, either fit with sinusoid or FFT filter that, but it was not very conclusive. And the strategy we use now is to remove this noise by taking every point and computing the medium noise around the window, with the window around it in time. And we do it for each channel and each time bit. So this is a very long way to remove this noise, but it's quite effective. So the game is to find the optimal window length. So again, if it's too long, we can see here that the small microphonic pattern remains. And if it's too small, once again, okay, everything is removed, but maybe also the signal is somehow affected. So we have a value in between for the reconstruction, and we can see here on this, on the waveform that at the end, after the microphonic in green, the waveform is almost flat and everything has been removed. So one way to see how the filtering worked is to look at how the value of the pedestal RMS after each filtering stage. And we can see that at first we had a pedestal RMS of around 1.8 ADC, and after the filtering down to 0.5, 0.6, so almost a factor of 3 decrease of the pedestal RMS. So this was for a subset of the data, but now we can look at the full event, completely cleared from the noise. And maybe there is some tracks here that we couldn't see before, but we can see now. And the game now is to find the hits. So what we have, as I said, is this array containing the data and another array telling whether or not one point is data or noise, the region of interest. So we can take a look at what this region of interest here is at this stage of the reconstruction on our analysis. So if you compare with previous plots, you can see that everything that should be considered noise is actually considered noise. But what we want to have now is hits. So actually, what we have at this point is just a collection of points, but the hit is actually has a certain shape with a length and a height and so on, and everything is important to reconstruct for the analysis afterwards. So what we will have to do is to find a long sequences of consecutive truths, and within this sequence find whether or not this is compatible with a hit, or if it's just random points that could be signaled. So there's an algorithm that we have developed that recognizes the shape of a hit, its peak, its length, and so on. It can also recognize if there is, for example, 2 hits very close to each other. So it's a bit long, so I didn't put it in the notebook, but I've put a simplified version of it. And okay, sorry. And we can see the result here. So for each point, we have now a box that defines where the hit starts and stops, and the dot is the hit maximum. And we can see that this simplified version is not optimal, because here, for example, we should have 2 hits that are very close in time, and it didn't work very well. So in order to show you the rest, I import all the hits that are found by the more complex LARDON, and not this the simplified version. And we can see it here, all the hits that are found, and we can zoom into if you want. And at this stage of the analysis, of the reconstruction, I have converted channel and beam time into actual position. So that's why we now have only one box for view 0 and view 1 and no more CRPs. And now, from this collection of hits, we want to find 2D tracks. So we do that with using a Kalman-like filter, and it works like that. All the hits are set in an R3 index. And we do that so then after we can choose a hit and find out who are its nearest neighbors. And in order to find a track, we have several steps. First, we take one hit still available in the index, find its neighbors. To initialize the Kalman, we fit a line with its surrounding neighbors, and then we propagate that with the Kalman filter. So at the last point that belongs to the line, we search for its nearest neighbor that are not yet attached to the track, and we try to test whether or not this point could belong to the 2D track with the parameters. And we compute a chi-square for each point, and if it's below a certain cut, then it's accepted, and this is how the track propagates. Once there is no more hit close by, then the 2D track has been found, and then we can go on until there is no more hits available in the index. Once we have found a track, like this one, we run an MST graph on it with all the hits to try to identify delta rays, and they are spotted by the fact that a delta ray is potentially attached to a graph vertices, so a point that is linked to here. Not just 2 hits, but 3 hits. And here we have found 2 potential delta rays in this example. Okay, so the result on the events that I've been showing you from the beginning. So the dots here are all the hits that are found, and the lines is all the 2D tracks that have been found by the code. We can see that it works quite well. It's not perfect. For example, here there is a problem. For some reason, the filter chose there's 2 tracks that cross, and the filter chose the wrong part of the 2D tracks. So it's not completely perfect, but in other cases of tracks that crossed, the filter did not make mistakes. So it's good, but perfectible. And from this collection of 2D tracks in each views, then now we want to build 3D. So what we do is we take one track in one view and try to find who could be its best match in the other view. So a best match is based on track timings. It should start and or ends at very compatible times, and the charge that has been collected in the 2 views must be balanced, must be almost equal. So every track gets a best match on the other view and vice versa. And if 2 tracks have same best match, then we can build a 3D track out of it. I hope it's clear. And here is the result from the event that we have looked so far. And the thick lines are all the 3D tracks that was found with one color in one view is the same, they go together. So this one goes with this one. And here you can see in 3D how well, you can play with it and look at the 3D version of the event we have been looking so far.
Lara, just to let you know, you've got about 10 minutes left, and there's a handful of questions for you. So feel free to bounce between that or finish up like how you want.
Just to, in terms of, I will quickly finish. In terms of running time, it takes about 20 seconds to reconstruct an event, where the microphonic filter is the longest, and the second one is to build the R3 index for the hits. And just before, because I like this one, if we look at many events together and superimpose them and look at all the 3D tracks, We can see, and here we look at the detector from above. We see the details of the detector and this 72 amplification device that we have set. And in particular, we can see the screws and the high voltage connector and the protective layer. You can compare that with the picture on the inside. And we don't just do, this is a theta phase space of muon like tracks that we have reconstructed. And finally, it's not just to do 3D, but also calorimetry that you didn't explain. And here we can look at how much charge we collect as a function of how long the electrons have traveled in liquid argon. And we can see a decrease due to the impurities in liquid argon. And it's a result that we were expecting. So in conclusion, it works well. And okay, I will look at the questions.
Okay. Thank you very much, Laura. If you want to walk through the question.
So, do you use this sort of interactive plotting and widget and presentation of the results within your collaboration? No, actually, I think I was one of the first to do a notebook rehearsal talk in DUNE, and it confused many people, myself included. But it was cool. I see a lot of bits of code. Are you somehow wrapping it all into domain-specific library to make it easy for colleagues to use and leverage? I'm not sure I understand the question. Here I put a lot of code to have the beautiful plots and everything, but I don't know. I'm not sure I understand the question.
We can take it offline.
Okay. Do the optimal denoising peak finding parameter change from run to run? If yes, do you have to find them by hand each time, or is it automated? So far, no. We try to not change them too much, but it might be needed actually. And in such case, by now it would be by hand. But it's true that an automated version would be optimal. But yeah, not yet is my answer. How do you calibrate your detector geometry, or is the installation misalignment irrelevant here? I guess you mean the two projected view. Well, by construction, they're orthogonal, so the geometry doesn't change. And in any case, yeah, if there is some tiny displacement, for example, in the two subplanes I've shown, I don't think it would be that much relevant with the data we have collected. Have you done this analysis for ND with DUNE 4 or only with ProtoDUNE? So far it's only with ProtoDUNE, and so far ProtoDUNE dual phase, but we, for some reason, the dual phase this technology has been changed to something different, so we have to adapt it. I'm not sure for the near detector, but maybe for a single phase or for the one who knows the vertical drift. It seems that machine learning would be very well suited for this task. And do you have any experience with that? Yes, of course, but there are some people working on that. And not so much for the dual phase, because you have different gains, and maybe training the machine learning could be complicated. But as I said in the conclusion, for example, at some point we wanted to try to identify the hits with machine learning or pattern recognition, for example. So this could work. So does it work for single phase? Not yet. And if such case, what would be the change? So for single phase or vertical drift, there is 3 views. So you need to adapt the 3D matching code to have a third projection. And the shape of the of the hits are different because there is an induction layer. So it needs to be adapted to work for single phase vertical drift or other geometry, but it's not impossible. It's just some work to do. And is LARDON packaged? No, but available online, yes, on GitHub.
Not sure. Yeah, there was is this last question clear? I mean, I guess you talked about it.
Yeah, I think it was related to would it work in single phase or
okay.
this kind of things. I think.
Okay. I apologize slightly because I maybe rushed you a little bit on the last couple of slides, including if there's anything you want to add that you had to skip or go quickly over, certainly feel free to.
But yeah, no, the conclusion. So okay, it was in my conclusion. It can be adapted to other design and will be, and there are some parts of the code that we also maybe need to further optimize, like the running time or the accuracy of the reconstruction. I've shown you one example where the 2D track filtering failed. And yeah, and if you think 20 seconds is long for data like that, the official code is much, much slower. And yeah, and yeah, one point is it's a great tool to quickly test different kind of algorithms, much faster than the official code. But that's it. Yeah.